Hello friends, welcome to lecture series on essential mathematics for machine learning. In this lecture we will see that if a general nonlinear problem is given to you, then how we can solve that problem if it is a convex programming problem. Okay. So, this is a general constraint optimization problem which we have already discussed, in which we have to minimize the function f, which is the objective function subject to g I x less than or equal to 0 I from 1 to m. So, there are m number of constraints. Okay. So, here we are assuming that f and g I for all I are defined and continuously differentiable functions. Okay. Now, the necessary condition. The necessary condition means that suppose a point x bar, suppose x bar is a point which is feasible means satisfy all the constraints and is a local optimal point for this problem P 2. Then what are the conditions that x bar will satisfy? So, those conditions are called necessary conditions. Okay. And here these conditions are called Karush-Kantakar conditions, KKT conditions. Okay. And a point which satisfy all these conditions is called KKT point. So, what is the theorem? Let us read out the statement. Let x bar be a local minimum point of the problem P 2 at which the basic constraint qualification holds. What do you mean by basic constraint qualification? Basically, these are the additional requirement which are required in the problem, so that the multiplier corresponding to the objective function is non-zero. Okay. We want the multiplier here it is 1, this 1 is coming only because we have applied some constraint qualification on the problem P 2. So, basically constraint qualification means that these are the additional requirement on the problem P 2, so that the Lagrange multiplier corresponding to the objective function is non-zero. Okay. So, holds. Then there exist multipliers also called KKT multipliers. KKT means Karush-Kantakar multipliers lambda I bar I from 1 to m such that the following conditions hold. So, these are the following conditions which must be hold, and these conditions are called KKT conditions. So, if x bar is a local minimum point of this problem P 2, then these conditions hold. But these conditions are only necessary condition, these may not be sufficient. So, what the additional requirement, what is the additional assumptions which must be required on f or g i's, so that these conditions become sufficient. Sufficient means that if we solve these conditions, if we solve a point, if we solve these inequalities and a point x bar will satisfy these inequalities, that will be a local optimal point of the problem P 2. So, those conditions are basically called as sufficient conditions, and the additional assumption is that f and g I for all I must be a differentiable convex functions. So, basically if the problem P 2 is a convex programming problem, then these conditions, then a point will satisfy these conditions will be a local optimal point of the problem P 2. That means that these conditions become sufficient. Okay. Then x bar is basically not only local, but it will be a global minimum point of the problem P 2. So, the proof is very easy. See, if you want to show the proof, see what are the KKT conditions. What is the problem P 2? The problem P 2 is basically minimization of f x subject to g j x less than or equal to 0, j from 1 to m. Okay. F is a function from R n to R, and g j's are the other function from R n to R, j from 1 to m. Okay. Now, we have to show that a point which is a KKT point, that means satisfy the KKT conditions, Karush-Kantakar conditions, then the point will be a global minimum point of the problem P 2. And of course, problem is convex programming problem. So, let us try to prove this result. The proof is easy. See, if you want to show that x bar is a global minimum point of the problem P2, then what we have to show? We will have to show that f x bar is less than equal to f x for all feasible point x of P2. This to prove, because we have to show that x bar is a global minimum point of the problem P2. That means, you take any feasible point, and for any feasible point of this problem, f x bar should be less than equal to f x. And given it is given to us that KKT conditions are satisfied, and the problem is a convex programming problem. So, what are the KKT conditions? So, let us go to the first KKT condition. The first KKT condition is gradient of f x bar plus summation I from 1 to m lambda I bar, it is I, lambda I bar gradient of g I x bar is equal to 0. This is the first condition. So, now this implies, so we know that x bar satisfies this condition. Okay. So, this implies we can use this as gradient x bar plus summation I from 1 to m lambda I bar gradient of g I x bar. So, if it is 0, then this will also be 0, okay, where x is any feasible point of the problem P2. Now, this further implies gradient f x bar whole transpose x minus x bar plus summation I from 1 to m lambda I bar gradient g I x bar whole transpose into, so into x minus x bar should be equal to 0. Okay. Now, since function and constraints are convex, suppose this is equal to this, this is equation 1. Now, since f and g I for all I are convex, so by the convexity definition, we can say that f of x minus f x bar is greater than equal to gradient of f x bar into x minus x bar, and also g I x minus g I x bar is greater than equal to gradient of g I x bar whole transpose into x minus x bar. And this further implies, this constraint further implies, this inequality further implies, now since lambda I bar, see, since this lambda I bar is greater than equal to 0 for all I, so we can say, we can multiply this by lambda I and sum up all the constraints. So, what we get, I from 1 to m lambda I bar g I x minus summation I from 1 to m lambda I bar g I x bar is greater than equal to summation I from 1 to m lambda I bar gradient of g I x bar whole transpose x minus x bar. Suppose this is 3. Okay. Now, you add 2 and 3, 2 and 3, add 2 and 3. So, what we get? We left with f x minus f x bar plus this is summation I from 1 to m lambda I bar g I x minus summation I from 1 to m lambda I bar g I x bar is greater than equal to. So, what we are having in the left hand side? In the left hand side, we are having this transpose x minus x bar plus this transpose x minus x bar, which from 1, from this 1 is equal to 0. Okay. So, we can directly write this is greater than equal to 0 from 1. Okay. Now, again you go to KKT conditions, lambda I g I x bar is equal to 0 for all I. If it is 0 for all I, that means sum is also 0. So, sum is also 0, that means that means this quantity is equal to 0, okay, because it is what? It is lambda 1 g lambda 1 bar g 1 x bar, lambda 2 bar g 2 x bar and so on up to lambda m bar g m x bar, and all are 0. So, sum will also be 0. So, we left with this finally gives f x minus f x bar is greater than equal to summation I from 1 to m with negative sign lambda I bar g I x. Now, what this x is? This x is a feasible point of this problem P 2. So, if it is a feasible point of this problem P 2, that means this constraint are satisfied for x, and lambda I bar are greater than equal to 0 for all I. So, that means that this expression is less than equal to 0, and with negative sign this will be greater than equal to 0, okay, because g I x is less than equal to 0 for all I, and lambda I bar are greater than equal to 0 for all I. So, this implies summation lambda I bar g I x are less than equal to 0, okay. So, hence this is less than equal to 0, negative will give greater than equal to 0. So, what this implies? This implies, so I am putting it in a bracket. So, hence f x is greater than equal to f x bar for any x feasible to the problem P 2, and this implies x bar is a global minimum point of the problem P 2. So, what we have shown? We have shown that if a point is a KKT point, that means satisfy the KKT conditions, and the problem is a convex programming problem, then that point is a global minimum point of the problem P 2. Now, convexity is an important condition. Without convexity, we may not say that point is a global minimum point of the problem. Suppose you have this problem. To understand this, let us take this problem. This is minimization of minus x 2 subject to these two constraints. So, let us see what this problem is. It is minimum of minus x 2 subject to it is x 1 square plus x 2 square minus 4 less than equal to 0, and second is minus x 1 square plus x 2 less than equal to 0, this problem. Now, let us write the KKT condition of this. So, how to write the KKT condition? The first condition is gradient of f x plus summation lambda I from 1 to m, gradient of g I x should be 0. This implies this is g 1, this is g 2. So, gradient of how many variables? 2 variables. So, what is del f? So, square is not there. So, gradient of f x. So, first with respect to x 1, it will be del f by del x 1, del f by del x 2 plus will come here actually lambda 1 times gradient of g 1. So, del g 1 by del x 1 plus del, so this is not plus, this is a vector. So, this is del g 1 by del x 2 plus lambda 2 times del g 2 by del x 1 and del g 2 by del x 2, which is equal to 0 0. This is by the first constraint, first KKT condition. Now, this further implies what is del f by del x 1? 0, del f by del x 2 minus 1 plus lambda 1 times del g 1 by del x 1 2 x 1, it is 2 x 2 plus lambda 2 times minus 2 x 1 and g 2 is 1, which is equal to 0 0, and this implies 0 plus 2 x 1 lambda 1 minus 2 x 1 lambda 2 is equal to 0, the first constraint, first equation. The second equation is minus 1 plus 2 x 2 lambda 1 plus lambda 2 equal to 0. So, these are the two constraints which we got from the first KKT condition. What are other KKT conditions? Let us quickly see for this problem. The other KKT condition is the second one is the feasibility condition, that is x1 square plus x2 square less than equal to 4 and minus x1 square plus x2 less than equal to 0. This is a feasibility condition. And next condition is the complementary condition. That condition is called complementary condition, lambda I g I x equal to 0. So, lambda 1 g1 is this condition equal to 0 and lambda 2 g2 is this condition equal to 0 and lambda 1 lambda 2 greater than equal to 0. So, these are the various KKT conditions for this particular problem. Now, let us check whether 0 0 is a KKT point or not. KKT point means it satisfies the KKT conditions or not. So, if you put x1 0 x2 0, so 0 0 equal to 0. If it is 0, then lambda 2 comes out to be 1. So, lambda 2 is 1. Okay. So, I am putting x1 equal to 0 and x2 equal to 0. So, this implies lambda 2 is 1. So, 0 plus 0 less than 4, true. 0 0 less than equal to 0, true. 0, if it is 0 0, that means it is non-zero. So, that means lambda 1 is 0 and 0 0, this is 0, this is 1 and 0 0 equal to 0. So, and lambda 1 lambda 2 are also non-negative. So, we have shown that 0 0 satisfy all the KKT conditions, but still 0 0 for this problem is not a global minimum point. What is the reason? The reason is that this problem is not a convex programming problem. Why? Because you can see if you draw the graph of this problem, the graph of this problem is, you see x1 square plus x2 square less than equal to 4. This is x1, this is x2, less than equal to 4 means inside this circle, and minus x1 square plus x2 square less than equal to 0 means this parabola, and outside this parabola, that means inside this circle, that is this region. So, 0 0 is clearly not a global minimum point of this objective function minus x2. You have to minimize minus x2. You have to minimize minus x2 means you have to maximize x2. So, maximize x2 will be where? Maximize x2 will be at this point or at this point. So, this point clearly will not be a global minimum point of this function. However, it is a KKT point, and the reason why? The reason is because this feasible region is not a convex set, or you can say that this is, or if you find the Hessian of the second constraint, Hessian of the second constraint del square of G2 is minus 2 0 0 0. So, this Hessian is not positive semi definite, that means the constraint G2 is not a convex function, that means this problem is not a convex programming problem. So, what we have concluded? We have concluded that a KKT point will be a global minimum point of the problem P2 only when a given problem, problem P2 is a convex programming problem. So, that is a sufficient condition. Okay. So, here are few examples based on KKT condition. Let us discuss one problem, say problem 1. So, we have to show that 3 by 2 9 by 4 is a unique global optimal solution of the following problem. So, for first we have to show that the problem is a convex programming problem, then we have to write all the KKT conditions, and then we have to show that this point 3 by 2 9 by 4 satisfy all the KKT conditions. This is sufficient to show that 3 by 2 9 by 4 is a global optimal solution of this problem. So, let us try this problem. This is the same way we can try for this problem also. Problem is minimizing f equal to x1 minus 9 by 4 whole square plus x2 minus 2 whole square, subject to what are conditions? The first condition is x1 square minus x2 less than or equal to 0. Suppose this is G1. The second constraint is x1 plus x2 less than or equal to 6. The third constraint is minus x 1 less than or equal to 0. The fourth constraint is minus x 2 less than or equal to 0. Now, G 2 is linear, so convex, G 3 is linear, so convex, and G 4 is linear, so convex. Let us see for F and G 1. So, what is Hessian matrix of F? It is 2 0 0 2. So, this matrix is clearly positive definite matrix and hence convex. So, F is this is positive definite and this implies F is convex. Now, similarly find gradient Hessian matrix of G 1, it is 2 0 0 0, which is again positive semi definite what we have seen. So, hence we can say that this problem is a convex programming problem. Okay. Now, let us write the KKT conditions. So, what are the various KKT conditions? So, KKT conditions, the first KKT condition is gradient of f x plus summation lambda I gradient of g I x equal to 0. Here I is from 1 to 4 because there are 4 constraints. So, what is gradient of f x? Gradient of f x will be, you find the gradient of this f. So, gradient will be twice x 1 minus 9 by 4 twice x 2 minus 2 plus lambda 1 times gradient of first constraint, which is 2 x 1 for x 1 and minus 1 for x 2 plus lambda 2. For lambda 2 it is 1 1, for lambda 3 it is minus 1 0, for lambda 4 it is 0 minus 1 is equal to 0 0. So, this implies twice of x 1 minus 9 by 4 plus 2 x 1 lambda 1 plus lambda 2 minus lambda 3 equal to 0. The second will be twice of x 2 minus 2 minus lambda 1 plus lambda 2 minus lambda 4 equal to 0. So, these are the two conditions which you obtain from the first KKT condition. Next are the feasibility conditions. So, feasibility conditions are the same conditions, these are the feasibility conditions. Next are the complementary condition. So, complementary condition is lambda 1 time the first constraint. The first constraint is x 1 square minus x 2, this is equal to 0, which is equal to, okay, this is equal to 0, which is equal to lambda 2 times x 1 plus x 2 minus 6, which is equals to lambda 3 x 1, which is equals to lambda 4 x 2, and lambda 1, lambda 2, lambda 3, lambda 4 all must be greater than or equal to 0. Now, what to show? We have to show that this point 3 by 2 9 by 4 is the global optimal point of this problem. That means, it must satisfy the KKT conditions. Okay. So, so x 1 is 3 by 2 and x 2 is 9 by 4. So, you substitute. Okay. First you substitute it here. So, what is x 1 square? So, first you see whether it is feasible or not. Okay. So, first we will see the feasibility. So, 3 by 2 and 9 by 4, 3 by 2 and 9 by 4. So, you substitute 3 by 2 is greater than or equal to 0, 9 by 4 is greater than or equal to 0, 3 by 2 plus 9 by 4 is what? It is 6 by 4 plus 6 by 4 means 15 by 4 minus 6, which is less than or equal to 0, that is true. And x 1 square minus x 2, 9 by 4 minus 9 by 4 is 0, which is equal to 0. So, that means first thing is clear that this point is a feasible point. Now the other conditions. Now this is x 1 is non-zero and lambda 3 into x 1 is equal to 0. So, this implies lambda 3 equal to 0 and similarly lambda 4 is also 0 and x 1 is 3 by 2 and x 2 is 9 by 4. So, and this is this sum will be 15 by 4 which is not 6, that means this is not 0, that means lambda 2 will come out to be 0. Okay. For from this we cannot say anything, lambda 1 may or may not 0, because this is 0. So, these 3 we have obtained. Now, lambda 3 is 0, lambda 2 is 0 and x 1 is 3 by 2. So, from here you can calculate lambda 1. So, what will be lambda 1 from this condition? It is 2 into 3 by 2 minus 9 by 4 minus 2 into 3 by 2 plus 2 into 3 by 2 into lambda 1. These two are 0, which is equal to 0. So, what we have obtained from here? So, this 2 will cancel with this 2. So, this is nothing but 2, this is 6 by 4, that is minus 3 by 4 plus 3 lambda 1 equal to 0. So, this implies lambda 1 is equal to, so 3 cancels out 1 by 2. Okay. Now only one condition left, lambda 1 is also non-negative. Okay. Only one condition to check. So, 9 by 4 minus 2. So, let us compute it here. So, 2 into 9 by 4 minus 2, lambda 1 is 1 by 2, lambda 2 is 0, lambda 4 is 0. So, this is 0, this must be 0. So, let us check. So, this is equal to what? This is 9 by 2 minus 4 minus 1 by 2. So, this is again 9 by 2, then 9 by 2 minus 9 by 2, which is 0. That means, this condition is also satisfied. Hence, we can say that this point satisfy all the KKT conditions. So, hence by the sufficiency KKT conditions, we can say that this point is a global minimum point of this problem. Okay. In the same way, we can solve the problem P 2 also. You write the KKT, you first check whether it is a convex programming problem or not. If it is a convex programming problem, then you write the KKT conditions and try to find the point x which satisfy all the KKT conditions. That will be the global minimum point of the problem P 2. So, in this lecture we have seen that if we have given a nonlinear programming problem and it is a convex programming problem, then to solve such problems you just write the KKT conditions. Okay. Try to solve the KKT condition and a point which satisfy the KKT conditions will be a global minimum point of the problem if it is a convex programming problem. Thank you very much.